Okay, I'm recording now. Uh, okay, so basically, this is what we did last class. We had two links, L1, L2. Everybody understands how we got to this point to start with. Then y equals L1 sine theta 1 plus L2 sine theta 1 theta 2. And then we saw how we put it into the code and how we got the whole visualization, and so everything played out on a larger scale. If we're to add another link to this as L3, what happens? Now, some people solved it, but just in case, we want to see what happens again. L1, L2, then these are end effector. End effector is like the fingers, the palm, whatever. L3. In this case, we have theta 1. Let me make that bigger. We have theta 1. Now this crosses at this point, and this gives us theta 2. This crosses at this point, and this gives us theta 3. So now we have 3 thetas. I think I can make this bigger, let's say. Okay. And now we have 3 thetas. And if you remember what we did, we established our y, and then we established our x. We understood that from the end effector all the way down, we can literally break it. We can break it. The same thing for this point. We can break this point. We can break this point, and then we can break this point. Here to this place is what we are looking for. Big X. From this top to this bottom is big Y. And the point we are looking for is position X, Y. So it's the same thing that we did the last time. Here we can isolate this. Let me use another color so it's a bit easier. Here we have this triangle here. And then we can tell that we can get x1. You see there's another triangle up here. And from here, we can get x2. Now you can see there's another triangle up here. And then you can get x3. So basically, x will be equal to x1 plus x2 plus x3. It's the same thing we did the last time. Same thing happens for y. Y becomes y1, y2, y3. The problem now is, how do we find x? How do we find y? In this case, x1 would be L1 cos theta 1. X2 gets a bit tricky because you see there is this angle that we do not know. But again, if here is theta 1, then based on corresponding angles, here would be theta 1. So we can say x2 is L2 cos theta 1 plus theta 2. And then we talk about x3. Now we see we have this bigger triangle up here. And we see that there's this angle that we don't have. But this angle is correspondent to these two angles at the same time. So what we'll have is L3 cos theta 3 plus these two angles, this particular angle that is up here. This is just simple geometry and corresponding angles, in case you don't know. So it becomes theta 1 plus theta 2. Then if you simply rearrange, x3 becomes L3 cos theta 1 plus theta 2 plus theta 3. And then your big X becomes L1 cos theta 1 plus L2 cos theta 1 plus theta 2 plus L3 cos theta 1 plus theta 2 plus theta 3. If you repeat the same process for your Y, I mean, it's intuitive, you get this. Theta 1 plus L2 sine theta 1 plus theta 2 plus L3 cos, sorry, this is the sine theta 1 plus theta 2 plus theta 3. I'll show you someone's code. He actually did something like that. Now, who did that tax? I think it was Sanyade that did that. Was it him? Okay, he even had a folder for it, overdue. And then we have 3D. Okay, it wasn't here. Overdue. 2D. And then okay. Let's look at this. Okay, so we can make this. I can make this bigger, right? Okay. He defined the 3 links: link 1, link 2, link 3. And then this is what we are interested in. You notice this is L1 cos theta 1. And then he comes down. This is still L1 because this is still X. And then he has L2 cos theta 1 and theta 2. And he comes down here. And he has L3 cos theta 1, cos theta 2, cos theta 3. Like rather cos theta 1 plus theta 2 plus theta 3. So now you know that, okay, if you have one more link, you just increase the number you add to it, because look at the 4 links that he also did. He defined 4 links, and it's a very repetitive process. You have theta 1, theta 2, theta 3, theta 4. So if you keep on adding links, that's what you would get. All right. So I hope everybody understands. Yeah, very, very interesting overdue. Very interesting overdue. But I mean, it doesn't just come to you that this stuff is repetitive. You just have to try it. I mean, but now that you know it's repetitive, you might say, oh, okay, no need. But yeah. So at least now we know what happens when we have, yeah, Tracy.
So I have a question, and I'm thinking, I don't know if it's possible to have, let's say, over 20 links. So is that how you'll be repeating it?
Well, it's now a question of why would you want over 20 links? Because adding the number of links does not, I don't see what it really achieves. Yeah, because why would you have 20 links? Well, now the thing is that how you be repeating it? No, there are other ways to also get this done, and that's what we want to look at today. But even in that other way, the more links you add, the more repetitive it gets, right? But 20 links for what exactly? There's something that is called degree of freedom. Adding more links on two-dimensional plane doesn't necessarily give you more degree of freedom. I didn't explain degree of freedom and all of that because I mean you can't really learn everything at once, but just know that adding, except there's how you're adding the links, because now there are different types of joints. You can read that now: prismatic, revolute, helical, spherical. Spherical joints. Yeah, I think so. So there are different types of joints. So maybe if you have 20 links and you mix them in different kinds of joints, you can want to achieve maybe more flexibility, more dexterity. Mhm. But on a 2D plane, I don't see a use case where I just add in 20 links. So yeah, there's also something you can do. I mean, it's programming. You can write a program that creates a class each time you create a link, and that's going to sound nice for a tax actually. So you just specify how many links and it automatically creates a new class for each link using a loop or something, you know. It makes it easier. All right, so we've looked at the three links. We've looked at more links basically. What is next now is if you want to add more links, fine. If you want to look at more different things, choice is yours. This was not really part of what we plan to do per se, but we're looking at it either ways. Now, before I proceed, I want to give some things you should keep at the back of your mind. One, this is when it comes to 3D, it's highly mathematical and almost abstract. I won't say abstract because I would say spatial. Like you need to do a lot of spatial reasoning. You need to like try and visualize it. But I'll try and take away so many mathematical notations. We'll still end up with the same answer. I'm aware there are probably some people here that know the whole mathematics of everything, but I'm not going to, like for example, what we're about to do, we are supposed to use a lot of direction cosines, but I'm going to eliminate all of that. I'll try and relate it in a way that is very easy to understand, but we'll still derive the same stuff and end up with the same this thing. The second thing I want to say is you will be following it, right? You understand one step, you understand the second thing I say, you understand the third thing, but over time you somehow get lost. It's normal. You because like yeah, it is actually normal. You are going to follow. You are going to follow, and then all of a sudden you get lost. It happens. Try and call me back when you're lost. Immediately you get lost, just call me and I would go back. And you would probably have to watch the video more than once to get hang of it. So before going to 3D, I want to explain some key concepts. Perspective in everyday lives. The way you see something is different from the way another person sees it. The same thing in mathematics. Let me not say robotics. Mathematics generally, perspective matters. If I put a ball here, a ball for example, this ball is at this point, regardless of where we look at it from. Like the ball doesn't move from this particular point. It doesn't. But if you stand here, you can say that this ball is, let's say, 100 meters, and then you will now move up another 100 meters. So from where you are, this ball is 100, 100. That's 100 on X, 100 on Y. But someone that stays here might look at the ball, and maybe this is 20 and this is 50. You would have to move in the positive direction and move in the positive direction twice, and then you have 100, 100, he is going to have to move downwards, which is generally considered negative direction, and backwards, downwards and backwards. And for him, the ball is minus 50, minus 20. Now I want to take time to actually let you understand that perspective matters. And while I'm bringing this up, I've explained what perspective is, and look at it in the mathematical sense. Now I've used numbers. The same way, you here, let's take away this 100 and 100. Let's assume we don't know. We can say this to be x1, y1, x2, and y2. These are still numbers, but we're using letters now. Another thing we can do is, say we said this is a human being. Maybe this is your friend, and this is you. Let's convert that into a mathematical equivalent. And it's going to be what we call frames. If you hear of the word frame, frame simply, frame can be interpreted as axis. You've heard maybe in physics, inertial frame, non-inertial frame, things like that. So we'll replace your friend by a frame, and we'll replace you yourself by another frame. Now you are the one telling the story. So let's say you are the fixed frame, and your friend can be, maybe it's the other frame, whatever it is actually. Whatever it is the other frame. Now, so far we are following, right? So this is the point. There's another frame. There's another frame. Now let's assume we have your third friend comes in, and maybe your third friend is, I don't know, your third friend is, let's clean this frame. Your third friend could be here. This is your third friend. But we can make another assumption. In this place, this shows your third friend's y and x. Probably this y is y, the way he's facing, this is y direction, this is x direction. But let's assume your friend rotates, like your friend just turns around. For some reasons, he's not facing you guys. He turns around, and somehow this is y direction, this is x direction. Your friend. Now, if you notice, it's a bit skewed. It's a bit difficult to intuitively tell how far this place is from it, because like we've somehow rotated where your friend is standing, right? I mean, if it was in this case where we had our axis like this, we can go front and we can go up. But the moment we twist this, it's a bit tricky how to get things along. I mean, we could trace to this x-axis, and then we could trace somehow to this y, but somehow it's a bit confusing now. Now, whenever things get to this point where it's a bit difficult to explain intuitively or with common sense, we now employ mathematics. Okay, now why am I talking about frames? Let's forget this point. Let's now say the ball is here. You are here, and this place is exactly 200 meters from you. You want to tell your friend to pick the ball. Mathematically, if you tell your friend, go 200 meters in the x direction, that statement is correct for you, because this is you, this is your x direction, and if you go 200 meters, you get to the ball. But if your friend goes 200 meters in his own x direction, you end up here. I don't know if you understand. So bit by bit, we are building these layers. The problem now is, how can you tell your friend, bro, go to this particular location, assuming this location does not have name, it does not have house, it does not have any landmark, it's plain blank space. How do you now know? So you see what you now do. You say, okay, you can phone your friend, right? You somehow phone this first friend that is a bit closer, or rather, I don't know which is closer, but let's assume this is closer, right? You first of all phone this friend, and you ask this friend to tell you where he is relative to where you are. And this your friend is, let's assume, he is, we can say this is 130 meters, and then up by 120 meters. Obviously, we know that this is 100 and this is 20. Can I take out the sharing icon? Okay, sorry. Let's put that aside. So now we know where this other friend, or this initial friend, you know where he is relative to where you are. So this guy can now find out where this friend is relative to him. At least if you know where this friend is, you can now give him instructions in his own frame or in his own coordinates. The same thing, if this your friend knows where this your friend is, he can now give instruction to this friend in his own frame. I don't know if you are following. It's more like you want to relate information now. So now, instead of me saying 200 meters, it will be easier for me to know how exactly I need to direct this guy, because I know the position of this with respect to this. I know the position of this with respect to this. Now, slowly, we are moving from the whole common sense and the whole real life scenario. And if you somehow envision things properly, you would find out that because you know this your friend's location from here, we can draw a link. And because you can find this guy's location from here, you can draw a link. And now what we have is a two-link robotic arm and a point that it's supposed to be at. Link 1, link 2. Why am I going this route? Because the next things that we would bring up will have to do with understanding where the next link is, or where the joint is with respect to where another joint is. So what is the main problem with 3D? If we have our 2D link that is like this, link and link, what we normally do is we just draw this down, and this is X, right? This is our big X, right? Then these are X2, these are X1, and then we draw it to this side. This becomes our big Y, and this is Y2 and Y1. Why can't we do this for 3 dimension? Well, the problem is 3 dimension will quickly get complex, because in 3 dimensions we have obviously 3 axes, Y, X, Z. Now let's assume we draw our two-link robotic arm in 3 dimension. Now let's say we go up and then we go like this way. Hmm? We can, the problem now is where exactly would you trace it to? If we trace it down, we can get this, and maybe we can trace this down here, and then we can get this. Meaning, you notice here we have 1, 2, 3, 4, 4 variables. No, we have theta 1, and then we have theta 2. So there's 1, 2, 3, 4, 5, 6, 6 variables approximately. So for this plane, you're going to have 6 variables to solve for. And then you can still trace to this plane. Oh, like, don't also forget, you can trace to this plane and still have something like this. And then you have another 6 on this side. And then the same thing on this particular side. And then before you know, like, you have these very, very complex systems of equation that is difficult to handle. So now you see why this is called, what's this called again? Analytical method, or geometrical method. This is why this whole analysis will not really work. It's giving 360 movements, because now you're in real life. You can trace it to any of the 3 planes and it will be correct. But like, if you can solve it for one plane and it's not going to be solved in another plane, like, it becomes far more complicated that you cannot just use normal sine, cos. I mean, that's what we use, but like, you cannot just use normal tracing of lines to get it done. So this is what we are going to do. We are going to have to branch out a bit to another part of mathematics, and I will show you. Now let's just go to any page. We'll take it step by step. I will start from something we know, that's our known knowns for us, before we go into the unknown. Sorry, I will start from the known knowns before we go into the known unknowns. There is no unknown unknowns in this case, because like, we know everything roughly. Please, can you give a quick recap? Where am I recapping from? Like, how long? Side? About 5 minutes. I mean, 5 minutes ago, I was just explaining why we cannot use normal trigonometrical approach or analytical approach, because usually we work by tracing to the axis, but in this case we can't trace to the axis because we have a lot of planes, and where exactly would you be tracing to? You can trace to this plane, and then you have different sets of variables. You can trace to this xy and zy plane, you can trace to xy plane, but just know that it's going to be a mess to attempt to solve it like that. So what we are going to do is another kind of mathematics, right? Another branch of mathematics. And I said I don't want to just throw us into that branch of mathematics, right? Right. Usually that's how it is. They just throw you into a different branch of mathematics. But I want to link what we know into this branch of mathematics. Now, again, I told you something about x, about this frame of axis, this frame, right? And then I told you this is you, and then you also have a friend. Maybe his friend is facing this way, and then you have a point, right? You know that this, what is analytical? Analytical or geometrical is that method we've been using. That's what we used to solve the 2D link, the 2D problem. And I'm saying we cannot use that because that involves tracing out variables from the graph. But on 3D, you have most, like, you can trace to any of the planes and then you get a lot more variables to work with, and it gets super complicated real quick. It's even difficult on the brain itself to even try. And I don't even think there's somebody that want to attempt that kind of stress. So we just use a better mathematical approach. Okay, so moving on. We now have two frames of reference, you and your friend. I explained how this is you and this is your friend, and how these points will be different for both of you. People will interpret it differently, right? Good. Now, if you notice, from you to your friend, two things happened. There was movement in a straight line called translation, and then there was rotation in this direction. So if you were to get to your friend's position, you would have to translate, you would have to move forward and then rotate. This is pretty simple. Now, if we want to give some mathematics to this, we might probably want to simplify it. So let's look at a case where we consider only rotation instead of moving. Let's say, let's consider we're going to draw a very big axis, like, because a lot of things will fill up pretty quickly. So let's say, let's consider something like this. Oh, sorry, this wasn't intended. Straight line. Okay, this. And then this. This is the first axis. It doesn't really look 90 degree-ish, but yeah, just put this to assume 90 degree. So this is the axis, right? And remember, there is a point, and this is the point. Now, we said you and your friend, if you want to get to your friend's state, you would have to move in this direction and you have to rotate. Now, we've said we want to simplify it. Let's take only rotation and leave this movement. So if we do not move and all we do is rotate, we will simply have another axis that will look something like this. Going to look something like this. Where we have rotated by alpha. By alpha. This is our initial y. This is our initial x. This is our y prime and our x prime. Are we all following up onto these points? Later. All right. So moving on. All right, Tracy, what's up?
Yeah, I just wanted to make sure I understand. So the red marker is when L is right angle, right? At 90 degree. And then the black one is when it has rotated, right?
Yes. Now they are all rotating, so they will still be 90 degree because this y is rotating by alpha. This is also rotating by alpha. So the angle in between them will not be changed. Like they are all frames. Frames are
Yeah, I
always 90.
understand.
Yeah. Just to be sure, this is just the rotation. Now, what happens when you rotate? You see this point? Remember, I said the points would now be different for each of the frames, because the way you see it will different from the way your friend sees it. So those points now, let's see what those points really are. If we trace this, let's start from the red. If we trace this down to this point, what we get is px. Px, because this is the point on x. Now, if we trace to the y, what we get is py. Now, again, I said geometry is not enough, but just relax. I want to move from geometry into the next parts that we actually need. So we consider black. For black, it would be here, px prime. And then this would be py prime. Are we following? We're just basically getting our numbers from things, or getting our variables. Now, what we are looking for, what are we looking for exactly? We are looking for the relationship of these points to the two of these axes. Like, what is the connection? How can we find out how a point relates to two different frames? Because that is the first issue we ran into. If you notice, the first question, the first things that we brought up here, where is that? Okay, I can't really find it. Well, we're talking about your friend, having three of those friends and a link between them. The idea was how we can represent the positions of this friend to each other and then to the points. Okay. Now I want to do some mandatory things. From this place to this place is px, right? If I should drop this down, if I drop this down here and I link this together, you see that we have some kind of triangle already. This is a triangle. This is a triangle. Now, you see this angle here, this particular angle, alpha. There is a rule again in trigonometry. You see this line and this line, they are parallel. That is, I mean, when I say these two lines, this line here and this line of this triangle, they are parallel. They don't meet. Meaning any angle, this line and then this line, they are also parallel. So when like set of parallel lines intersect, the angle that is formed here will be equal to the angle that is formed here. Because basically what happened was we had one parallel, another parallel, Then we now had one parallel and another parallel. And this angle is alpha. This angle formed is alpha. This is and again, theories from geometry that are like proven. So if this place is alpha, you can quickly tell that this place is sine. Yes. Okay, we have this line up here as py, p prime y, because you know this side is py prime or p prime y. Corresponding angles. Yeah, I think that's corresponding angles. That's what I previously explained. I think it's corresponding angles. Uh, I know it's not alternate. It could be corresponding. Yeah, it could be corresponding. Let's see. Just a quick check. Just in case you want to like references. Yeah. It's corresponding. That's it. Oh, it's a YouTube video. Sure. But that's basically it. Corresponding angles. Yeah. So okay, back to this. Now this is py. You can see now that this line would be py sine alpha. That's this particular line here, because this is py, this is alpha, and then normal trigonometry, meaning this particular place is py sine alpha. Moving forward, you see there is this alpha that is here already. This alpha already is here, and earlier we established that this point is p prime x. We've already had it labeled. That means the overall length from here to here is p prime x. Yes, what's up? Cos alpha. Yeah, I can see hand raised. What's up?
Yes, good evening.
Yeah,
From the complementary angles, right? The
I think it's
complementary angles, I
corresponding.
think it, sorry, hello, can you hear me?
I think it's corresponding.
Sorry, the corresponding angles. Can you hear me? Hello?
Okay. Yeah, I
Yes,
can hear
for
you.
the
I can hear you
corresponding
clearly.
angles, we have been able to identify alpha, right? We identified
Yes.
alpha. But
Yes.
now the axis, the x-axis, you said it's py sine alpha. I was
Yeah.
thinking the
Okay.
x-axis should be py cos alpha
Cos.
and not
Okay.
sine
Good.
alpha. Yes,
Good.
not
Now
sine alpha.
let me take out this particular triangle for you so you look at it. Again, axis is relative.
Yeah.
This is py. This is alpha, right? This triangle is correct, right? This triangle that I just is the same as the one on this point.
Okay. With reference to we are referencing that angle. Sorry. Okay. Correct. I
Yeah.
understand.
So now you
Understand.
understand why it's sine, right?
Yes.
Because it's now it's opposite the angle. Good. So far we've brought this out. What we can now tell is that tx, there's a relationship. Yeah. More people raised hand. What's up?
Hello, Bakke.
I'm with you, Emmanuel.
Please come again. How do you get your P prime X cos alpha?
Okay. Good. Now let's clean this triangle. I shall call this area my triangle area because we'll be bringing out a lot of triangles. All right, let's say triangle area. Now for the cos, you can see this triangle. I'm trying to trace it, the red dots. You see the big triangle here. If I bring it out, that's like one of the biggest triangles from our graph. We have alpha, and you see this point was initially we've marked it out as P1x, or Px prime, and then cos, which is adjacent, here becomes P prime cos x or cos alpha, which is this whole length, at the bottom. Do you understand now? Manuel, do you get? Okay, I can't get the feedback from you, so okay, yeah, you understand. Okay, Said, what's up? Okay, so I'm moving on. Nobody hands is raised. Okay, so now you can see that somehow we've gotten a relationship between the two frames, the points, unlike alpha. We have px. This px is from another frame, which is the normal frame. We have p prime, which is from the rotated frame. And here what we can see is p prime x cos alpha is equal to px plus p prime y sine alpha. Does this make sense? Rewriting px would be equal to p prime x cos alpha minus p prime y sine alpha. Now we'll hold this and we'll keep it somewhere. Now we want to derive something again. You can see this height up here, this particular height is p prime x sine alpha, right? And then you can see this particular height, this one again. You notice here was p. About victory, why for loss now? It's now why I say I should just notice say they lost. Better talk. Why you don't lost now, blood?
Okay. As you brought out that triangle, everywhere just starts to the blur.
Wait, which of the triangles? Let me know.
The one by the left.
But that means you lost it like minutes ago.
Yes.
Look, the moment you feel you are lost, say something. Because I want to carry as much as I can carry in the little time that we have. Okay. So again, okay, this will also help other people that probably didn't get it. So let's reiterate. All right. So going back in time to the previous commit. The reason why we brought out that triangle was because we wanted to prove this p prime x cos alpha that we said. This came because of this big triangle. So when I wrote it, someone asked that how did I get p prime x cos alpha? And that happened because I isolated this big triangle. Let's call it triangle A. So I know, okay, this is triangle A, this is triangle B. I isolated this big triangle A into something like this. And then we know that the hypotenuse of the big triangle is p prime x. We know that the alpha is there. So the adjacent, which is the x, would be p prime x cos alpha. So that is how we got that there. So that's where the big triangle came out from. So yeah, good. So now having seen that, okay, yeah, we know where the big triangle comes out. The rest is easy. P prime x cos alpha equals px plus p prime y sine alpha. And then, you know, simple mathematics, p prime x cos alpha minus p prime y sine alpha. This is what we need. And then we just want to just take a break. Now, I now said that we've gotten something. If you notice, we're not doing x and y, and the ones on the x, the one on the y, like we did the last time. This is a different approach. So I said the next thing that we will now realize is, you see this height? Yeah, Victory, what's up?
Okay, in this last formula you just wrote, p prime x cos alpha, which is what we just got after we took out the big triangle, is equal to px plus p prime y sine alpha. Why is it not minus? Or am I looking at it wrongly?
I think you are. Because from here to here is px. From here.
Okay. Yeah, I missed the reference. I was looking at the end.
Yeah.
Okay.
Yeah.
Thank you.
Okay. Can I move on? All right. Now, this horizontal, like this vertical rather, this, let me clean it so I can make another emphasis on it. Yeah, Tracy, what's up?
Okay, can you make your pointer a bit bigger so that we know when it's moving? It's very tiny.
That should be something I can configure. Is this something I've tried configuring? No. Is this something I want to do right now?
No, not this guy. Your pointer, the thing you're using to write, it's red in color.
Yeah. I know. I know what you're talking about. I know what you're talking about. But I have not messed around to know where that is. See. Does it make it bigger? This is like the thickest option I have.
Okay, it's fine.
I'll
Bitch.
I'll find a way around that. So now that you've mentioned it. Okay, so moving on. I was talking about these points. Okay. I think I've cleaned something. Here was p prime x. Somebody's hands. What's up?
Sorry, Chief. I still don't
Yeah.
see how it is P. I still don't see how it's a complementary angle, because I mean, if you do the math. Hello, sorry. Hello, can you hear me?
Yeah. I didn't say
Yes,
complementary, corresponding. The
corresponding. I still
corresponding.
don't see how they are corresponding angles. I mean, the alpha at
Yeah.
position X and the new alpha at position x, at position y1 x1, right? So I'm still struggling with that because if you rotate them, the alpha there is supposed to be, you rotate them, it's supposed to be 90 degrees minus the alpha, right?
Okay, let me get a
Yeah.
clean sketch for you to see something.
Okay.
And the moment it doesn't make sense, call me. Y, X, right? So if we rotate the whole, like we have the whole plane, if we rotate everything, everything moves together. So let's make this X prime alpha, and let's make this up here. This isn't really so neatly done. Make this up here. Okay. Y1 alpha. So far, this is fine by you, right?
Yes, yes.
It's fine by you. Do you also agree that there's a 90-degree angle here and there's a 90-degree angle here?
Yes, correct.
Okay, nice, cool. Now we're talking about a point on this place, right?
Yeah.
And if I trace that point to x1 prime, I get something like this, right?
Yes.
And this is parallel to this, right?
Yes.
I can choose, for the sake of clarity, to extend this to infinity.
Okay.
Now you see we have two parallel lines. Now
Yes.
I can now say from here, remember what we drew was a consequence of tracing down to x. We had to trace down to this point at the point, right?
Yeah.
And now we have something like this, right? And I can choose to
Yes.
extend it to infinity, right?
Yeah. Yes.
So now let me take out unnecessary details.
Oh, okay, okay. I see it now. I see it now. I
Yeah.
see.
So
I see it now. Thank you.
yeah,
Sorry,
I
man.
I I,
I
I had
see.
I had I had to do this. I remember the first time I saw it, bro.
I see it now. Yeah. Thank you.
Yeah. So yeah. So good. Now, where was I? Ah, okay. So I'm moving on to the next side. Um, we have this. Let me clean that. So now remember we drew this. Why you hold up? Ah, okay. Now we have this down here. And remember this hypotenuse is still P1x, right? The hypotenuse is still P1x. So this horizontal would be px prime rather sine alpha. That makes sense, right? And now we want to check for this point. That's this height. This height would now be py prime cos alpha, meaning the overall height from this point down to the ground which is PYU, that overall height is PY. That PY would be equal to PY prime cos alpha plus PX prime sine alpha. Is it understandable?
What angle are you referencing? Sorry.
I mean, we're still on alpha, this particular angle.
Okay, see the angle. Okay.
What we're doing is bringing out two fundamental equations that we need. Let me see if there's anything in the chat. Okay. Now we have two equations. And scroll up. Those two equations, let me get these out. Those two equations are Px equals Pix cos alpha minus Pi or P prime Py equals Px prime sine alpha plus P prime cos alpha. Okay, re-explain the second. All right. But you got the first one side. Yeah, good. I have a good number of people following. So let me take out some details. Right? Let me take this out. So what we are looking for now is this Py. You can see we've gotten something that relates Px. So it's Py now. And Py, if we look at the graph, if we get this height, and then we get this height, we can add it up to get Py. And from what we are seeing, this initial height here, that's this up one, is the same as, remember this small triangle that we got? Let me bring out that triangle again. It's a small triangle up here, where this angle is alpha, and the hypotenuse is Py. And we earlier established that the opposite is Py sine alpha, meaning this height that we're interested in is Py prime cos alpha. So what that means now is this height we are looking for is Py prime cos alpha. Whereas this height that remains is the same as this height here, the same thing. And this is even easier to find because this triangle A is the same thing as this triangle A. Like I just brought it out some steps back, where we have alpha, we have P prime X or Px prime, and then the height that we are looking for would be Px prime sine alpha, hence Px prime sine alpha. Great. But you good guy. Just say got it. Okay, this is where we are.
Wait,
Now,
sorry. Please go back. Go back. Wait, never rush. I beg.
some hands were up. Some hands were up.
Where did we get P1Y sine X?
Yeah, that the cos part, the Py, is it Py cos alpha?
Yeah.
Yeah, I didn't get that part. Oh, I
Okay.
understand the py cos alpha.
You understand py cos alpha?
Yes, I understand py cos alpha, but I was lost around where you got the other side.
Okay. So let me draw a new. Let me just. I'm going to draw a fresh one just to answer this question. But let your brain not deceive you that it's a new problem. It's the same thing. So I'll just draw it afresh. Make you say go back like mad. I don't know. Okay. So we'll go again. Alpha. Alpha. Point in question. You say YouTube. Okay. At this point, remember, everybody knows so far that we have gotten our px. At least it was not that hard. Just have it in your mind that is solved. Now we'll look for the py. And what we can see is this height. It will have a hand in what we are going to do, right? So hold on. Let me now redimension the diagram. I mean, this one looks like scattered, no, scanty. So let's like populate it a bit with things that we might need. Remember, if I draw down here, it's px. But if I draw to this point, it's p prime x, right? Remember, we established earlier that this angle here is alpha. And we now know that there exists a triangle here. So this triangle is our point. So the point P does not rotate. No. From the example that I told you, the ball is where the ball is. The ball is where the ball is in space. Like it's completely there. Like it's where you are relative to the ball. The P does not move. You are just rotating only the frame. So, well, this particular triangle that I just made is our focus. If I should trace this, which is something we did before, we find out that this point is py prime, right? Meaning from here to here is py prime. So this triangle that is causing headache, let's bring it out and let's focus on it. P prime y and alpha. What we are interested in is this height, because we are looking at for the height things now. This thing is the same as rotating the triangle like this. So putting here as alpha, putting here as p prime y, and then looking for this point. It's the same thing. You're just maybe rotating it. It depends on how you want to see it. So now you find out that our py first we've gotten this one, this side, as p prime y cos alpha, because this place is p prime y cos alpha. So we first gotten p prime y cos alpha. First. You can now see that the next thing that is remaining is this other height. And this height that I just drew is the same as this height. And now let's come now, we have another triangle. Let me use another color so I'll highlight that new triangle. This triangle is the new triangle. And with this new triangle, you know that this is the new hypotenuse, this side, and we've established it to be P prime X normally. So this particular height now would be P prime X sine alpha. So you know that we've gotten this height and we have this height. So Py would be P prime Y cos alpha plus P prime X sine alpha. Yes, equivalent to getting, yes, Garrett, yes. So, yeah. Yeah, it's more like using two triangles to get the sides. Yes, that's it. That's it. That's the idea. Okay. So, moving on. We have two equations now. More importantly, what are we going to use the two equations and do? And that's the journey I'm taking you on now. So, two equations that doesn't really solve anything yet. Px is equal to P, sorry, what was the equation? Just to be sure. Okay. P prime X cos alpha minus P prime Y sine alpha. Py equals P prime Y sine alpha plus P prime Y. What? Sorry. P prime X plus P prime Y cos alpha. Let me just make this clearer with my handwriting. Cos alpha. Okay. This is what we have. Two equations. And this is where we have we're going to create like a bridge from one form of mathematics into another form of mathematics. Now, what we are going to do is we're going to move from geometry into matrix with one very dubious move. We know how we normally multiply matrix, and probably some people must have forgotten how to multiply matrix, right? But I would decompose it and I would multiply it again to show you the same thing. This matrix Px Py is the same as cos alpha minus sine alpha cos alpha P prime X P prime Y. And now I'll decompose it. This Px is Px equal to multiply matrix, you take this row multiply by the column. So it is actually P prime X cos alpha, which is this times this, and then this times this, minus P prime Y sine alpha. Same thing for the bottom. Py, which is, let me use another color, which is Py is sine multiplied by the first value and then the cos and then the second value. So it's P prime X sine alpha plus P prime Y cos alpha. It's the same thing. But the trick is in decomposing it, like somehow using your brain to like reverse engineer it. And then this is what we need. Why? Because I'll tell you why. The first problem we had with three-dimensional space is that we have too many variables to manage. Like on one plane, we can get like 6 variables. So by the time if we trace it down, if we trace it to like 3 different planes in 3D space, that's like, isn't that 18 variables? And that's like so many equations. But now we have represented 2 equations and like 4 variables in one single equation using matrix. So this popular thing known as rotation matrix, this is how you move from geometry into it. So now we're not going to be tracing triangles. Probably doing some more sick stuff. Moving on. What we have is px py equal cos alpha sine alpha minus sine alpha cos alpha p prime x p prime y. This is called rotation. This is called the rotation matrix. This is the position matrix. So I want you to see it as, remember we said 2 things must happen. If I want to move from, remember that example I gave, to move from this point to this point, 2 things must happen. I must translate and I must rotate. somewhere left. I saw when he left the call, probably network, and then he came back and boom, we're in another set of questions. We moved we moved from one dimension of mathematics into the other. it's like you blink and you're lost. Okay, how did I reach Abby? Magic. So now you see math is very crazy. Usually they don't do this link for us. No, hold on. We're not doing about Z yet. That Z will soon come, but the rotation our recording the come to me. Okay, let me take it again from where we are all familiar with, where we all stopped. We stopped at, let me just get a new page. We stopped at px equal p prime x cos alpha minus p prime y sine alpha, and then py equal p prime x sine alpha plus p prime y cos alpha. Remember how we did all the triangles and bringing out triangles and everything? This is how we got here. 2 equations, solid. Now I said for 3 dimensions, we don't use, it's difficult to use an analytical method, because in order to bring out all these things, we use an analytical method. We drew lines, we drew graphs, we drew triangles, complementary angles, and all of that. If it's in 3D space, you get lost. Yeah, Olamide, what's up?
Yeah, I have one question. I understand the whole calculation part and everything, but I'm a bit confused. Like, unlike the 2D, when you explain like if we have like a fixed point and 2 links, do you get? And it's been, I can like see it visually, like okay, like if we have like a robotic arm or something. But in this context with 3D, the way you explain, I'm still kind of
I know even
lost.
in 3D. We're not even in 3D. Have you seen a third dimension here? We're not yet in 3D.
No, like this part you explained, the introductory part here, maybe
Yeah.
lost. I may be lost with the explanation with the introductory part.
Okay. Is it the idea of okay?
Yeah, yeah,
Hold
like
on.
the idea.
Okay. So from what you earlier said, I think you understood having a ball somewhere and you being here, and then let's say another of your friend is your friend, and then your last friend is here. You remember you understood this analogy, right?
Yes, yes.
And this is where we drew the robotic arm, right?
Yeah, yeah, I understand.
Now hold it. Probably you lost network at some point or something, but hold that thought. That thought is very valid. Now I said this is the bigger picture. So let me strip down some things for you. And I said, okay, let's remove this. Let's make it simple. Instead of having the full robotic arm, let's have you and what? And your friend looking in another direction. So you see, we've removed one of the friends in the middle, right? So to understand how to get your friend, where your friend is from you, if to understand that connection, we would have to, let's say this is you. I want to end up exactly as your friend. You would have to first of all move to his points, which is translate, and then you would have to rotate. What I'm doing is I start from the whole idea of the robotic stuff, the robotic arm, and I'm like bringing it step by step so you know why we are getting to where we are getting to. Now I said, okay, we have to translate and we have to rotate. But based on want to do this thing mathematically, let us make things easier for us. Let's start with only one kind of motion. Let's start with translation. Sorry, let's start with rotation and not translation. So let's think of what is the mathematics behind rotation. We'll come to translation later. What is the mathematics behind the rotation? And I said, you have this, and then instead of translating or going anywhere, instead of moving away, just stay where you are and rotate. And this is like the whole mathematics now that governs that rotation. You know that okay, this is how we are. We are still like building things up. You understand? Olamide?
Yes, I'm with you.
So you are with everybody now. You know why we are moving through the bush.
Yeah, yeah, I understand now.
Okay. Now the part that took us back to begin with, how we moved from one field of mathematics to another field of mathematics. Okay, so I said to an experienced person, it looks obvious how we can pivot this equation from geometry or analytical that it is into matrix. But now there is no way that I cannot instill in you that skill. It's something that, how do I put it? You see it, it comes to you. But I can do it and undo it, and then you see it's the same thing. Maybe next time you'll be able to pick it up. Question: does the position matrix handle linear motion x while rotation matrix handle? See, oh boy, you good, but you are too fast. You just wait, just wait, just chill. It's either you've done it before or you've somehow seen it in the previous one, but just chill. So now, I said let's do the matrix now. Px py. Don't ask how I got it to, but I'll show you why it's correct. Becomes cos alpha sine alpha minus sine alpha cos alpha p prime x p prime y. Now, why is it correct in the first place? That is because Let me get another color. Px, if we take Px, to multiply matrix, you know it's row multiplied by column. You will do row and you will do column. So you first do cos multiplied by this. So that is Px multiplied by cos. And then you do plus this multiplied by this. And then it's plus minus sine alpha times Py. And that gives you this whole thing minus Py sine alpha. And now if you do for Py, which is the bottom, it is this multiplied by this, which is P prime x sine alpha plus this and this P prime y cos alpha. So do you see that while it's not so mathematical to decompose it into a matrix, you can undo it and it's the same thing. So do you know how the whole matrix came into play now? Good. Now we have successfully gotten out of trace here, bring out triangle. We've successfully gotten out of that. All those is Leonard Euler and the fathers of mathematics, all them Archimedes, them that's their field. We've gotten into a place that is a different field of mathematics. Sadly, Leonard Euler is in all fields of mathematics. It was too good. So either ways, Px, Py. We are now dealing with the matrix cos alpha, sine alpha, minus sine alpha, cos alpha, Px1, and then now somebody said something in the comments. What does this matrix really mean? What does this, hold on, let me get this like this. Okay, now what does this matrix really mean? Remember we said we have 1 point here, and then we want to get to another up here, right? This is 2D. We've not added z-axis at any point in time. What we want to do now is to translate and then to rotate. And from what we've seen, if this is our initial normal x and y axis, and this is our x prime and y prime axis, translation is handled by this particular matrix, because this like shows the definition of where this x is and where this y is, whereas the rotation by alpha is handled by this particular matrix. When I mean handled, don't think of it as don't try and put some kind of common sense into it. When I mean handled, know that rotation is specified by alpha. You cannot see alpha inside here. You can see alpha inside here. Now movement is x and y. You cannot see x and y inside here. You can see x and y inside here. So you know what matrix is responsible for what. And when I mean responsible, we'll still get back to that one now. Okay, up until this point, everything has made mathematical sense, right? All these things that we are trying to do, we are trying to see a new form of mathematics that will help us solve the 3D problem. Now, the next approach that we are going to take is, let us fully understand what we are doing so far. I will draw a link. a link we're all familiar with, a link that we know the answer to, right? And I would attempt to use this our newly found method to solve it. Because each time you find a new method or you develop something new, you ought to be able to find a way to like verify that this is correct. If it works in 3D, it must work in 2D. So just keep this arm here for application purpose. Remember, don't try and connect the if the dot connects in your head, fine. It might connect right, it might not, but don't bother yourself with connecting the dots. We'll get to it. Remember I said P X P Y equal cos alpha minus sine alpha sine alpha cos alpha P X P Y prime prime. What this means is this is our P X. Yeah, Samuel.
Oh, sorry about that. So I wanted to ask, all this mathematics we were doing from the beginning, it was just to get this matrix, right?
Yes, yes. So this is what happens in school. This is a very, very unconventional way of teaching it. What happens in school is they teach you the geometry, and then when you come to the next class and you want to do 3D, they throw a matrix at you and tell you that's a rotation matrix. And then you learn from the beginning, you learn from the rotation matrix. So that's how it is in a lot of textbooks. Let me not call names. It's not as if it's bad, it's okay, it's good. But if there's one thing I tell people that work with me is understand something intricately. And when I mean intricately, like they should wake you up and then they tell you why is this. Be able to explain why. Because frankly speaking, the people that became like the very best in whatever they did, Laplace and Simon Laplace, then Euler and the rest, they intricately understood what they were doing. So they were not just saying it is rotation because it's a rotation matrix. So at least if anybody woke you up and like, okay, where did the rotation matrix come from? You know where it came from. If there's any need to make some genius innovation about it, at least you fundamentally know about it, right? So that's just the whole idea. I mean, I could have started the class by throwing the matrix at you and telling you, hey, this is the matrix, but no. So okay, so now we're at the matrix. Good thing everybody is fully into this point. Now I want to now explain what this matrix mean. Let's now use like let's put some form of intuition and common sense to it. I spoke about frames, and I said frame is like you or the axis. That's a frame, not axis. A frame has 2 axes or 3 axes, but like frame is like frame XY. This frame means this matrix here is the matrix for the frame. The frame PXY. Then this one is the matrix of the frame P pi XY. And then the whole equation explains where this whole frame is relative to this frame. Because the first problem I explained with those 3 frames was if you can know where the first friend is relative to you, and you know where the last friend is relative to the first friend, then you can actually create, using mathematics, a way to tell the last friend to pick the ball. It's like creating this connection. And it's that mathematical connection now that we have seen. This is the matrix that sort of represents that. But now we want to further, we want to further simplify this thing. Now, we have what is called a matrix, and then we have what is called a transformation. We want to now do something that if, remember we said this is the equation that is governing the two frames, right? The equation governing the two frames. If I now add a third frame, how do I now add this third frame into the equation? Will I put another equal to somewhere? That alone is mathematically incorrect. So you start thinking, how can we add another frame? Because somehow it feels as if we are solving the problem, but along the way we've run into another problem. But thankfully that has already been solved. But now you probably would have gone home thinking of how to add another frame, because this equation is just for two frames. So in order to add another frame, we have to find a way to press this thing, this particular equation. We have to press it into one, so that we know that, okay, if we add another frame, it's just to join another one. If we add another frame, it's just to join another one. Like, we have to find a way to compress it into something like one variable or one matrix that give birth to homogeneous matrix, homogeneous transformation, where for let's now use the real links. Let's use the real links because it's about to add up. Let's take this fixed point as O as our origin, and then this joint is, let's call it A. The joint to OA is link 1, right? This ending is E based on end effector. AE is link 2. So we want to now do some form of another branch or another extension of mathematics, whereby instead of representing two frames in one equation, we represent two frames as one matrix. Let us assume that this place is O and this place is A, like we earlier said. Here remains our theta 1. We trace up here theta 2. Nothing has changed so far. I'm looking for a way to compress this now that will not be so. Okay, let's write it out again. Writing it out again just reinforces the knowledge for us. So we can say OX, OY. We know what OX and OY is equal to cos theta 1. We've removed alpha now because now we know the rotation is theta. This is the frame, the O frame. The next frame is this one. Sorry, brother. Sorry to bother you again, sir. I can't really go and go. Okay. So recapping. It's not as if I've said anything different, but recapping. Again. Okay, fine. Let's get a clean slate. Clean slate. Let's pick a point that everybody is comfortable with. We are at this point, px py equal sine alpha. Cos alpha minus sine alpha, cos alpha, and then we are at p prime x, p prime y. Okay, and then I said what this means is this is your px axis, this is your p prime xy axis, and like this equation is what relates this whole moving and rotating, right? Good. The next thing I said, let's now apply it to like the link. So if we if we draw our link, if we draw our stuff from here to here, theta 1, the joint, remember, theta 2. Now, let's give some labeling. This is origin O, this is like A, and this is E, end effector. It can be B, whatever. Now, we can have an axis here, right? We can now have another axis. If you notice, this axis has been moved and rotated, and then we can have another axis up here. Just hold on. Now, instead of using T and P prime, let's deal with O and A. We will now have OX, O A, sorry, OX, OY would be equal to cos theta 1 minus sine theta 1 sine theta 1 cos theta 1 AX AY. You cannot see the screen. You have to go and try and log out and like come back again. Now, what we are going to do now is, the problem was, how do we now add another axis or another frame? We cannot do equal to and mesh it. We can't just, we need to find a way to compress this whole thing into one matrix. And that is where we now come up with something called a transformation matrix, where we say transformation, or let's say movements, the translating and the rotation, everything is called transformation. The whole movement from A, which is down, to O, that's the whole movement, would be equal to, now let's find a way to sandwich these two things together, and we'll do it this way: cos theta 1 minus sine theta 1 AX sine theta 1 cos theta 1 AY. We have a new matrix now. And what I'm going to do now is, this is allowed in, if you've done matrix before, it's allowed. Even when you are doing matrix reduction, Gaussian and the rest, where you are eliminating rows and just canceling things, it's allowed. This is matrix maths. You can just merge it together. But what we want to now do is, if we leave it like this, there will be some issues that will come up. Those issues are completely unknown to you at this point, because like you've not run into those issues yet, but we are going to run into it. So in order not to run into it, let's just like add some knowledge that we can explain later on. I can explain later on if we have that time. 0, 0, 1. This 0, 0, 1 took me months to know why it was there, right? Why? Because just know that it's to make the matrix complete. The actual reason we are going to find out if we choose to continue. Maybe somebody says, okay, Alpha, I want to know, but first understand this. This is the matrix called a transformation matrix. What does this matrix mean? If you notice now, we are getting far away from the whole idea, and we're going a bit deeper into the matrix math. This whole matrix is the same thing as this equation, which is the same thing as this thing that we're talking about, moving from one frame to another. So now we have transformation as one matrix. And the good thing with transformation matrix is you don't need to start tracing where your X is, where your Y is, where your whatever. We are still in 2-dimensional. We'll come to 3-dimensional, but I'm explaining the transformation matrix with what you already know, so that moving on will be easier. Now, scroll up. how does this help our life? Now we know what the transformation matrix is. So now let's redraw and let's do things properly. If you notice, the position of cos minus sine, it doesn't change. You just have it in your head that that's the transformation matrix because we've already derived it. We didn't just spring it up on you. Now, let's go with our robot again. O, A, and the vector. This is L1, L2. Forward kinematics, as you all know, is how do we change different positions to get to the ending? Like if we set different things, what would the ending be like? So that is why the overall transformation we are looking for on the long run is the transformation from E back to O. Remember, the one we did earlier was transformation of A to O. So we are looking for E to O. Now that transformation from E to O is the transformation from A to O multiplied by the transformation from E to A. The way I visualize it in my head, we move from E to A, and we're at A. A here is same thing as A here, and then we're now moving from A to O, totaling the motion from E to O. So O E equals TA dot A E. I think I'm going to pause here and ask if you people are following. Okay, so I'm sure people are following. Great, great. On our stability thing. Anyways, these are transformation now.
Please recap. Please recap. I wasn't seeing this. Please.
I know when you complain you're not seeing the screen, but that's too far back and time is greatly against us and we're almost done. So
sorry, I don't understand the TOTE part.
Okay, just the TOTE part, right?
Yes.
Okay. I can recap that because that's like 2 minutes back a bit or so. So remember when I said, okay, you know what TAO means, right? Okay, explain T again. Oyana. Matter go tough this night. And like this is the last thing. Like just understand the T. The rest is easy. Okay. Man. I want you guys to just the equation part. No wahala. I will still explain the T. T means transformation. Transformation means transformation is okay. Remember I said this guy again. We are translating. Translate is to move forward, and we are rotating. Transformation is simply rotation plus translation. So it's like combining all the things we have, all the long equation. Remember we had this guy. So this, everybody knows that this is the translation and the rotation. This part is the translation, this part is the rotation. So everybody knows this. And then we just basically combine it together. We just took this put it here, took this portion, put it down, and added 001. The 001 that we added, somebody say, why is not 000? I can we'll explain that later, but just assume you know it as 001. It's extremely complicated to explain right now for you. So we are at this, and then there is O and A, meaning I explained this is the O side, this is the O, this is the A side. The equation initially was how do we move from how do we define A with respect to O? That is A with respect to O, and this is the A and this is the O. So we just simply carry those two things, A, O. Now, let me clean all of this for the T, and let me show you without the robots, without the link. Now, this is what I'm saying. Okay, good. We have this as our origin. We have this as A, which is another this thing, and then we have this 1, 2 as E. Now, transformation allows us to move A to E, E to A to O, E to A to O. We want to know E from O. The one that connects this to this would be T, E, A. The one that connects this to this would be T, A, O. Meaning, the one that connects this directly to this would be T, E, O. And one way to do that, or the way we would have to merge them, or like the operation to connect them, is T, E, O equal T, A, O multiplied by this. So I like to visualize it as you move from E to A. And then this is your A, you're at A now. You now move from A to O. Overall, you've moved from E to O. Do you understand the T thing now, roughly? That's Ajiri, that's one person. Sonia the victory. Olamide. A little Tracy. A is at the middle. Yes, A is at the middle. Okay, Sonia has Olamide has replied. Good, Tracy. Okay. Sahid. Normal level now, normal Sahid now. Okay. The good thing about transformation matrix is you don't have to start drawing many lines as to where what is. You just know the matrix and you're good to go. So I'll show you how we now use it, because when we talked about how we now use it for the actual forward kinematics, this is what we want to do. I will start by emphasizing or reiterating that TAO is equal to cos theta 1, y theta 1. Here is theta 1. Remember, so cos theta 1, sine theta 1, 0, minus sine theta 1, based on the formula we already have. It's not like I'm springing it out from anywhere. And remember, AX, AY, 1. The question now we need to ask is, what is AX and what is AY? AX, as you know what AX is, this is O and A. So if you are drawing here down, you know this is your x, this is your y. I mean, you don't really have to start mapping it out. Automatically, you would know that ax is L1, which is the link length, cos theta 1. Is there any disputes? I'll assume there's no disputes. AY is L1 sine theta 1. That being said, we can also say TEA is equal to cos. Now, there's another theta, but in this case, theta 2. The rotation is theta 2. Cos theta 2 sine theta 2 0 minus sine theta 2 cos theta 2 0. Again, what is supposed to be on this side? What's supposed to be on this side is EX EY 1. But in this case, our EX is simply L2 cos theta 2. Common sense again. I mean, we've been doing X and Y for a long time. And then L2 sine theta 2. Are we following? Okay. And then the rest is easy. The rest is just matrix multiplication. For the sake of multiplying plenty sine and cos, let cos theta 1 equals C1. Because by the time you start writing plenty cos and sine, sine theta 1 S1 cos theta 2 C2 sine theta 2 S2. What other weapon do we even need to know, Seth? We need to know. No, don't worry. Let's just keep going. I think that's something that will be fun to discover on the road. So CEO, remember the formula OA EA, normal drive. So we have our stuff. We have C1 S1 minus S1 C1. Yes, Suleiman, what's up? I can hear you.
In the second matrix,
Have I made a mistake?
can you hear me?
Yeah.
Can you hear me?
Yeah, I can hear you.
So in the second matrix, why is it L2 cos theta 2 and not as usual L2 cos theta 1 plus theta 2?
Okay, good question. This is because I want you to understand something. Cos theta 1, you do theta 1 and theta 2. If you remember the previous one, you do theta 1 and theta 2 when you are looking at that rotation with respect to the base. Do you know what I mean by that? Like, do you know what I mean by that, or I should further explain? Yes, he got it correctly considering the individual lengths, but there are different ways I can explain it, that depending on how you are comprehending the whole thing we are following. So I'm trying to understand how you see it.
Sorry, is this the triangle, the first triangle down, the one with the L1?
What?
Like, I'm trying to understand how you got the L cos theta part. Like, is this the L1, the triangle with the L1 part first for the top one?
Yes, now. Yeah. Well, I don't want you to see it as triangles. Yes, the second reference is A. Yes, because we are doing CEA, not CEO directly. So the first reference is O, A to O. The second reference is E to A. And the rotation of E to A is theta 2, not theta 1 plus theta 2. Theta 1 is only A to O. Did you understand? Okay. Okay, Said gets it now. So somebody spoke again. Olamide, are you following now?
Yeah, I'm with you.
Finally. Okay. So all I'm doing now is rewriting it with things that we can easily use to fire down. And then here we have C2. You know, this is pretty much the same thing. S2, C2, 0, 0, L1, sorry, L2, C2, L2, S2, 1. And then the rest thing we need to do now is multiply, Abby. As easy as that sounds. Hold on. Sorry, it's a bit, I need to reply to this. Mm, mm, uh, okay, we're back. So now we are doing the multiplication, right? And what we can do from there is we're going to have this wide matrix. Let me make it wider. And just make it wider from here. Because from experience, this matrix cramps up a bit. Okay. So how to multiply it? C1, C2, C1, C2 plus C2, S2. Sorry, S1, S2, sorry. Plus S1, S2. This multiplies this is 0 plus 0. Now move on to the next one. S1, let me use another color. S1, S2 minus S1. Okay, it becomes plus, right? S2 plus who will now make a mistake like this? That's not the other multiplication. Sorry, this one is still correct though. This one is still correct. That's still correct. Okay, we go again. So this and this, this and this. So S1, S2. So it's minus C1 rather than 2. And then this one to this one down. And then it's minus C2, S1. And then this one is 0. So I mean this and this is 0. And I'll move to the next side. We use, I think I should be putting it so it's like in case you guys like will go over it 0. So we go to another color. Then we have C1 and this. That becomes C1, L2, C2. Yeah, what's up? Why multiply? Why not add?
Hello, can you hear me? Sorry,
I can
my
hear
mic was muted. The first result, the C1, C2 plus S1, S2, is not supposed to be the row multiplied by the column.
Yeah, row multiply column. Did I get something
Yeah,
wrong?
but yes, C1 supposed to be C1, C2 plus
Yeah.
C1, S2
Wait,
plus
hold
C1,
up, hold up.
S2.
Wait, hold
The
up,
first,
hold up. The very first row, first column, right?
yeah,
First row, first column, C1, C2 minus S1, S2.
minus S1. Okay, yeah, correct. Oh, yeah,
Yeah.
correct. I'm missing it. Okay.
Well, it's off. But you see, the thing is, matrix is difficult for us, but super easy for computers. Whereas, you see that trigonometric analyzing, we are drawing line here. The computers don't really know how to do that. So this is like super efficient for them. They just numpy. We've been using matrix. Even the last one we did, we put them in matrix, blah blah blah, that kind of thing. Okay. So nobody's going to ask you to do this by hand. Nobody will ask you. Tracy says you can't comprehend for that. No worry. The thing is, you don't have to learn how you don't have to multiply the matrix. In the real application, nobody multiplies the matrix. I just want to show you something that you would actually understand what's going on when you actually do the stuff that you want to do, the computers that you want to do. I mean, to me, I feel it's a shame that people use things without understanding them. And then when it breaks, you find out that you don't really understand it. You only know how to use it. It doesn't only apply to matrix or every other thing. So where was I? See. So I was in S1 to down here. So we now have minus S1 L2 S2. And then finally we have this and 1. And then we have plus L1 C1. Moving on, we now go to the second rule, and I'm not going to draw plenty lines, but I hand still up. You still want to ask something? Tikochi. Okay. So I'm not going to draw the many lines because now the lines are too much. Just try and follow it. Also, Tikochi, just focus in case I skip something because I almost like some minutes back. Okay, so speeding up S1. No, I'm on green. No, let's maintain yellow. So red. Hey, oh, run around again. S1 C2. S1 C2 plus C1 S2 plus 0. The next one becomes S1 minus S1 S2, and then we have plus C1 C2 runs down to 0. The next one becomes S1 L2 C2, and then we have plus C1 L2 S2. The next one runs up to 1 L1 S1. Now the final rule, this runs down to 0 completely because of the 0 down there. Runs down to 0 completely because of the 0. Does it run down to 0 completely? 0 0 0 0 0. And the next one is this here, 0 0 0 0. The last one is L1. And what we have here is L2C2 plus, this correct, L2S2. Is this correct? Is this correct? All right, let me double check.
I think it's meant to be 1.
Yes, it's meant to be 1. I just look at it. It's meant to be 1. That's very nice. Okay, so 1. And now this is where we have some little magic. If I should bring this out, this becomes cos theta 1 cos theta 2 minus sine that will be too long, extremely long. Let's leave it as it is. S1 S2 minus S1 S2 S1 C2 plus then here we have minus C1 S2 minus C2 S. Olamide, I think network took him out. He's going to ask us what happened now. So 0. And now here we can see that we can factorize some things. We can factorize L2 and then we're left with C1 C2 minus S1 S2 plus L1 C1. Then we can factorize L2 here. Then we are left with S1 C2 plus S1 S2 plus L1 C1 1. And remember something from trigonometry, this that we said sine theta 1 plus theta 2 is equal to sine theta 1 cos theta 2 plus cos theta 1 sine theta 2, which is the same thing as in our case S1 C2 and then plus S1 S2. Now cos theta 1 plus theta 2 equals cos sine cos theta 1 cos theta 2 minus or plus minus sine theta 1 sine theta 2. So this becomes C1 C2 minus S1 S2. What do we do with this? We simplify the equation we have before us. In order to do that, this place becomes, so anywhere we see hold on, I just scrolling so violently. Okay, so anywhere we see this here. So this is cos theta 1 plus theta 2. Simple substitution. Then we see this, which is this here, and it becomes sine theta 1 plus theta 2. And then this place becomes 0. And then up here, we can remove this minus out. Like we can take the minus out. We have S1, S2 plus C2, S1. And that corresponds with this. It corresponds with this actually. And then we have minus sine theta 1 plus theta 2. And then this at the bottom. All we need to do is just take this to the front. It corresponds with this if you check it. And then we have cos theta 1 plus theta 2. This place still remains 0. And then this is where we have actually the main thing. Because S1, S2, S1, S2. This becomes L2 plus theta 1 plus theta 2 plus L1 cos theta 1. And this bottom and then this part here is this, it becomes L2 sine theta 1 plus theta 2 plus L1 sine theta 1 1. This whole thing we solved is actually our transformation from E to 0. So what we are interested in, or like our confirmation that this whole transformation thing actually works, is, remember, transformation is the actual meaning of the transformation is this part, this up part is rotation, then this part is actually where our x and our y is. Remember, the side that is responsible for x and y and the side that is responsible for rotation, meaning our x and our y are all respectively equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2, L1 sine theta 1 plus L2 sine theta 1 plus theta 2. Do you guys actually remember this that we got before? And now I have only 2 people following, 3 people following. So there's something I made mention of in the Python class where I said if you do that print f, if you want to print one variable, just do print variable because it's simple and straightforward. If you now want to print a variable and a word, and maybe many variables and many words, you now do print f and then you print. The f allows you to do more. But if you are doing just one variable, it's a lot of stress to print f, because when you put f, you put a column, you now put parentheses. So you type extra 3 characters just to print one variable. It doesn't make sense. But if you want to print many variables and many strings, you can go through the stress of typing those extra 3 characters. This is an example of a 2D with 2 links. It might not make sense to go through the stress of having to do this, but it works. It would work. The main stuff now is doing it for 3D, because trying to do 3D with just normal tracing and bringing out triangles would not work. So this is the whole transformation that is used in 3D. If we want to do this for 3D, we would have to extend it, but that can be done in another class. That's why I said we have 2 classes, one for the what's up?
Yes, sorry, I'm trying to get, this final formula, does this represent, like, the robot configuration? Because we have because we've said it has rotation, and then we've identified the x and y. Could that be the translation, and we say
Yeah.
that's it?
If you notice, the first thing we did, the very first exercise we did was this. We were interested in just px position, right? That's the very first thing we did, and that position is what we have gotten here. When we first started, we're not concerned about rotation, because on a 2D, I mean, if this guy wants to rotate, the whole link just ends up rotating either ways. Depending, like for this configuration we have. But on a 3D, bro, there's so many possibilities for rotation. That is why it's compulsory to be able to represent rotation for the 3D. So this is the maths. Now let's do a little bit of the code. So I prepared two codes. One that will help you understand rotation, another one that will help you for the transformation. And
Well, I've not finished. I was not understand. I was not understand this one on paper. I want to carry us to code. Asana, please. Who is agreeing with me? Please. Let's. I beg.
but it's tough. What don't you understand? Just tell
See,
me. Tell me what don't you understand.
this whole plenty numbers happening here. The course, the C1, C2, that thing that you're doing, I have to go and watch it again and follow the line one by one because I was not just following. So if you want to now
Well,
carry us,
at least you know what you have to go back and watch. So, I mean, for the sake of the people that are following, I have to proceed to show
no
them,
problem.
because don't worry. I shall reach out to you after I've sent the recording. I'm sure you understand. So, okay, I would stop sharing from this. I mean, it's the same thing on Windows or Linux or whichever, you know. It's just, where is the thing? Okay, and I would share here. Okay. Okay, so I'm coming. I'll make my screen bigger. I know about that. I just want to locate the actual code we'll be working with. Rotation. Okay, this is okay. Mhm. Now, based on the rotation, what the code do is simple. Let me run the code. So let's start from there. So you see what I had in mind, what made me to write the code. Oh, okay. I don't know if you can see this. Okay, let me do it this way. Let me terminate it and let me clear. Okay, good. So I want to run the code now. And I see it's asking me, what axis do I want to rotate? In this case, we didn't talk about axis. We didn't get to that, but let's just put Z. But now, what angle do I want to rotate? And I put, say, 30 degrees. It computes the rotation matrix for me. Now, this one is not really any, it's I only came here to show you guys something. I came here to show you the implementation. Yeah. See, this is cos, and then this is minus sine, cos 001. This whole format is something I need to further explain how we got to this. But I want to tell you that even if I dismantle ROS and I go to the package move it, which actually does the kinematics and everything, you would see things like this. And as a matter of fact, I'm going to do that. I just thought of it, and I mean, you would actually see that these things are what are like under the hood. Now you can see this is another kind of rotation matrix We see here, this is like different. This has the one in the middle. This has the one at the extreme. Different things for different purposes. But this is because it's on a 3D. Let's leave that aside. Then we have the homogeneous, the transformation that we did. This particular code allows us to visualize transformations. Let me quickly make a few modifications to it, because this is in 3 dimensions. We didn't get to 3 dimensions, so let me eliminate some of its dimensions. You don't really have to like understand why or what exactly I am doing, but like I'm eliminating some dimensions, and I want it such that we use the variables we have. Let me use, instead, what did we use in class? I used E to O, right? E to O, that's what I used in class. So I would now, I can eliminate this whole matrix out of it. How many matrix do I need? I need just 2 matrix. I need just 2 matrix, right? Yeah, I need just 2 matrix. So I only need E, I only need A to O, and then I only need E to A. And then what I need at the end is O to E to be equal to this multiplication. And then I print it out simplified. And yeah, good, great. This is what I want to do. And I'm going to come here and what is our O to E? Our O to E is L1, L underscore 1, and cos. Should I use cos? Should I not use cos? L underscore 1. Let me get my, it's cos L underscore 1. Cos theta, cos theta, cos theta, cos theta. Ma underscore 1, L underscore 1, L underscore 2. Opposite. L underscore 1 underscore 2. And then L underscore 1, L underscore 1. And I eliminate this row because we didn't do anything like that. And then I include this row, okay? And I reduce this dimension. All right. So I delete this. I have L underscore 2. I have L underscore 2. I want to see what this should give me if I run this code. Okay, it attempts to give me a transformation matrix based on the inputs that I give. Oh, my transformation matrix was this. Can I do multiply by cos theta 1? Then this multiply by sine theta 1, because that was what we used in actuality. And then cos and sine theta 2. I make that changes to I eliminate this. Okay. Z. Being on this spot is like witchcraft. Okay. Hopefully this works. Ah, great. It worked. So this particular code is, I did it so that you can like visualize what happens when you play with different transformation matrix. And what I did, let me clear it. What I did was, I know that I want to do T O to E, and I know TO to E is TOA and then TAE from what we did in class. So what I have to do is I just have to define my TOA and TAE. And my TOA is this matrix. This matrix is exactly the matrix we used. It's just a bit scattered. If you look at sine theta 1 minus sine cos theta 1 minus sine theta 1, sine theta 1, and then L1 cos, L2 cos, L2 cos, L2 sine, all of that. And it's pretty straightforward. The rest of all these things, I documented it so you can see how to run it. So this doesn't really solve directly. It just gives you the transformation matrix that you need to solve. So yeah, that's pretty much it today. A lot of information in one class. So there is no tax. As a matter of fact, trying to understand this on its own is a tax. So yeah, it is what it is. There's going to be a lot of confusions, but that's why we have a therapy session tomorrow instead of a continuation, right? So that is it. The code is in the repo. Feel free to play with it, whatever. There is no tax today. See joy. So yeah, some of these things is at the end we are going to see how when we're doing Ross this weekend, and when we now look at how the code works, you would appreciate the maths that happens underneath the hood. Why do you need to know maths? I don't know if anybody is interested in one real life story that happened to me last week. Last week, a particular company, they want, so they have their humanoid robots, these robots that like human beings now, and they want to be able to measure certain quantities from the walking and the running. They want to measure things like the distance between the foot. They want to measure the speed. They want to measure stance. They want to measure cadence. They want to measure there were 32 different parameters they wanted to measure, right? So 32 different parameters. And last week, so they reached out and they said, we have only one sensor, which is an IMU, which is an inertial measuring unit. What IMU will do is IMU can measure the position and the orientation. Orientation is the rotation and the position is translation. This is related to what we are doing. IMU can do that. It's common knowledge. But from this IMU, they want to get 32 variables from measurements. Now, IMU would give you 9 variables, 9 measurements, X, Y, Z, for acceleration, for velocity, and for position. But it's X, Y, Z, that's 9 measurements. So if you want to solve other things, the same way you have position of O and A and E, and you want to solve how to move it, the same way I had 9 measurements to work with, and I had to think of how to calculate 32 out of it. You would quickly realize these things, they don't just have a library that says this library computes this library computes that. You are now in front of developing this thing. And jobs like this pay a whole lot because it's proprietary code. It's for the company. They want to sell this. They want to use, and they're like at the forefront of this stuff. So now you have to compute it. This thing took me into the depths of signal processing because you have to find a way to calculate different variables. I had to actually sit down, grab like my pad, read a lot of papers, see how to calculate different parameters from what before even starting to write over 2,000 lines of code. So right now the code is about 2,000 lines, but the conversation between me and the product manager is what's like the actual maths, the actual idea behind all these things. So you would have to know at some point that let me show you a post. I made that post, the mathematics of walking. That was something similar. That was something similar where we had to predict different things, or I had to predict different things about how it works. That is okay. This happened. Copy link to the post. You can look at it. Before I even started programming anything, you would have to understand it. So let me also drop it on the group chat just in case you can't see it from there. So it's not as if tomorrow nobody's going to ask you to prove transformation matrix. The world has gone past that. But understanding that you have to understand how things work put you in a better position when you get jobs and you're not copying and pasting things. So hey, I have a message. Where's the group chat? I think this is just easier for me to access from here because I have the group chat already opened on this PC. Yeah, great. What's up? Can see your hand, great. Just talk. Okay, so that's yeah. Nobody. This is not university. This is not school. You're not cramming this, or you're not having to know this. It's good if you know it and you can just give it out of your head. It's impressive, but this is just to tell you that you have to do this for other things that work that serve it. All right, so I think we can wrap it up for today. No tax. As a matter of fact, only 8 people have done tax 2. It's a bit too early to start losing so many people. But I know how difficult it gets. Okay, so our suffering continues in the WhatsApp group.